Okay, in this video we're looking at state transition diagrams and LTL, linear temporal logic. So it's a bit like assignment 10. I've got a state transition diagram and some LTL formulas, and we're going to work out whether or not these formulas are true on some or all of the paths of this state transition diagram, and whether or not we're going to talk about what paths make them false or what paths they're false on. Okay, so that's the starting state. Start there. Okay, so the first one says x and on the next state y. Okay, so for these you might want to check them yourselves, what you think they're going to be, and then check to see what the actual answer is on here. So first one, x and next state y. Well, the first x is true in the first state, y is true in the second state. Any path of this state transition diagram starts with those two states, therefore it's true in all paths, therefore it's true on some. Okay, nice, start nice and easy. Okay, next one, eventually z. Okay, so I've just noticed these cake, pie and apple over there. Okay, so let's talk about the state transition diagram for a second. Okay, so first thing I've done is I've just written x, y, z. I haven't written not z, not x. Okay, because we're in classical logic, we've got the law of extended middle, which tells us that if x is not true, then it must be false. Okay, so I just put the true things in the state transition diagram. Okay, so a little shortcut makes things look smaller. Okay, so let's imagine that this state transition diagram is the layout of a house with one-way doors. Yeah, a bit weird, but it is. Okay, and x, y, and z are things in those rooms. So in the first room, in the porch, you've got some cake. In the next room, you've got some pie. And then in these two rooms, you've got the unhealthy room, the cake and pie room, and then we've got the apple room, the gym. Okay, so we can think of these paths as walking around this house, and we're asking questions about what stuff we can eat. Yeah. So this one said, can I eat some cake today, and tomorrow can I eat some pie? Yeah, and the answer is yes, so we're happy. This one says, kind of, will I ever be able to, will I, in some time in the future, be able to eat an apple? Yeah. And for some paths, or we can see one path where this is true, if we go there, there, and there, it's true. Yeah. So, yeah. The next question, the all question, is would, however we walk around this house, will we eventually get to a room with an apple in it? Okay? And the answer is yes, because x, y, z, we get to one with apple, x, y, y and x, z. Okay, so we've done a case analysis on the possible path prefixes, the beginnings of paths, and they get to a z. So, yeah, we always eat an apple. Our dentists will be happy. Next question is a bit more complicated. It says, will it always be the case that I can eventually reach an apple? Now, this means will it always be the case whenever I'm in a room, can I get to another room with an apple in it? Yeah. So now we've got to think about starting in any room trying to get to a place with an apple. And this is reachability. Yeah. So the other thing to bear in mind here is that this always is an infinite thing. Yeah. So we need to have we need to consider all traces or infinite traces. Yeah. But we can see pretty quickly that this is true because all paths have to pass through this state infinitely often. Yeah. Because when they get to this state, they have to either stay in it, which means they'll be in Z, or they'll have to leave the state, but then the only choice is to come back to the state. Okay? So we're going to visit this state infinitely often, which means it's always the case that you'll eventually walk back into the apple room. So we're either going to be walking into our cake and pie room, eating some cake and pie, then going back to get some apples, cake and pie, apples, cake and pies, or we just might sit there eating apples Yep, or eat loads of apples, kick a pie, eat loads of apples. Always going to be the case that eventually we're going to be eating apples forever, infinity. Yep. So let's fill this in. The next one says eventually we'll always be eating apples. So this is different from always we can eventually eat an apple. This says there'll come a point when we'll eat apples every day from then on. Yep. Again, this is infinite, always, forever. Yep. So we can find one path where this is true. X, Y, Z, 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 forever. Yep. Now, the path X, Y, Z isn't a true path because we need Z to go on forever. It's infinite. Yep. And one thing people got wrong on the assignment here was not realising when they needed infinite paths. Yep. So it's true on that path. But in this scenario where we go apple, cake and pie, apple, cake and pie, apple, cake and pie, apple, cake and pie, yep, it's never the case that we're always eating apples. We're always having the alternate cake and pie, yep, or X and Y. So that's one path, yep, there, forever, where this isn't true. Yep, so it has to be forever. Yep. That's not the case. Okay, the next one says it's always the case that X implies Y. Again, forever, and this is true in all paths because X implies Y is true in all states. Yep, so okay, there, this is quite easy. Maybe I should do some more difficult ones. This one says always we eat cake or always we don't eat apples. Yep. So this isn't the same as always we eat cake or apple or no apples. Yep. It's always we eat cake or always we don't eat apples. Or yep. So always we eat cake fails here. Yep. So in room 2 we're not eating cake. Not eating apples. Yep. X, Y, Y and X apples or X, Y apples. Okay. So that doesn't hold. On any path. Yep. And the last one, we don't eat cake until we eat apples, is false. Yep. So we need not X to hold until Y holds. Y holds there, but not X doesn't hold there. Yep. Okay, so those are quite easy. Yep.